Уважаемые коллеги, мне предоставляет большое удовольствие предоставить слово нашему гостю, выдающемуся математику Шинтун Яо. Вот я специально начал по-русски, потому что сейчас я перейду на английский язык. На всякий случай мое произношение могут не понять. Dear colleagues, it's a great pleasure for me to give a floor to an outstanding mathematician, Шинтун Яо. He awarded with many prizes, Fields Medal, Oswald Veblen Prize in Geometry, Wolf Prize in Mathematics, and many others. He is an elected member of United States National Academy of Science, and he is also foreign member of our Russian Academy of Science. You are welcome, Professor Yao.
Yeah, thank you very much indeed. I'm honored to be invited by you to give this satellite conference for ICM. I was hoping to visit Kazan on the way to ICM in St. Petersburg, but it turns out, unfortunately, not possible. Both my teacher Chen and my former student Rick Chen was given the prestige Lobachevsky Medal in your academy, and I'm very proud of them. And indeed, Lobachevsky was a great geometer whose work inspired the great accomplishment of Riemann, whose work changed the field of human science, and especially general relativity. So indeed, according to Einstein himself, large part of general relativity was based on the works of Riemann and Newton. So this work today will explain some of the foundational works in general relativity that can be traced back to questions asked by Einstein and Newton in 1915. But there are also questions for geometry. General relativity has been a major motivation for the development of modern geometry. So I think they will closely linked something. This talk is on the mathematical part of general relativity. It's based on joint work with my former students, Ed, Ugloway, and also the student Jordan Keller and Mikai Wong. So the topic is on angular momentum. It will be a quantity measure something called now infinity, which I will discuss later. It measures the angular momentum of a confined area, like collision black hole, which is carried away by the gravitational wave. So potentially, with the nowadays major measurement that can be done by LIGO and all this big experiment, we can measure gravitational wave now. We hope to be able to measure angular momentum to verify how the angular momentum is carried away by gravitational wave. So it's important to understand what angular momentum is actually. Now, at now infinity, there's ambiguity. Unfortunately, it's called super-translator ambiguity, which causes major difficulty to properly define what angular momentum means. So I will discuss how we can resolve this problem using the theory of quasi-local conserved quantity that have been developed by Muda Wang and myself in the last 20 years. So this the super-translation ambiguity for angular momentum has been a major open question in the subject for around 60 years by now. So I'm kind of proud that this can be resolved recently. But before that, I want to do a motivation. First of all, how does Einstein motivate himself to go from Newtonian physics to general relativity? So these are physics which measures gravity and give a good description of gravity. And we know Newton's equation for gravity, as was written by Laplace, is Laplacian U equal to rho, where rho is the matter density of distributed matter, like galaxy, like stars, and all that. And then U is the potential created by this configuration of masses. And this is how Laplace write down the equation for gravity in this form. So Laplace invented Laplace operator. So this is what he did. Well, then in 1908, Minkowski written down a way to measure special relativity by a geometry. This is called Minkowski geometry, and it's governed by the Lorentzian tensor ds squared equal to minus dt squared plus dx squared plus dy squared plus dc squared, where t is the time, x, y, z are the space. So in this geometry, photon travel along null geodesics is very important. Photon travel along null geodesics. So when you measure things at infinity, you observe the null geodesics travel by photon. And the particles with non-zero mass travel along time-like geodesics. So this is a very spectacular interpretation of special relativity due to Minkowski. This led to a radical change of the concept of gravity, because this now finally make people understand special relativity going to general relativity. It has to go from 3 dimensions to 4 dimensions. Space and time cannot separate out. That's a famous statement made by Minkowski. From now on, space and time cannot be considered separate quantity. It has to be considered together. Well, once you put them together, this means t and x, y, z are kind of equal in many ways. So we have to be forced to look at a 4-dimensional space-time. Only after that, Einstein realized that in order to describe general relativity, you need a tensor instead of a scalar. So you look at Newton's equation, according to Laplace, is described by scalar function u. It's a function, single function. But now Minkowski's way of looking at things is looking at tensor now. It's a metric tensor. Well, metric tensor is reasonable, famous, or well known by that time after Riemann. Riemann did his famous work in 1854. So it's almost 60 years after Riemann. So based on this work of Minkowski and the equivalence principle, which says that physics, gravity or physical gravity cannot be depending on the coordinate change. So this is called equivalence principle in this form. Einstein therefore was looking for a tensor. Maybe I should not call T mu nu, it's called G mu nu, which is should be considered as a gravitational potential in space-time. So U should be replaced by a tensor. That's the conclusion. And this space-time is governed by the Einstein equation, written in this form, where R mu nu is the second differentiation of G mu nu, is a Ricci tensor. R is the trace. So the left-hand side is can be considered as an operator obtained by differentiate the metric tensor 2 times G mu nu. And this is very similar to the previous equation due to Laplace, is you differentiate the potential 2 times. So here we differentiate the potential G mu nu 2 times. You obtain the Ricci tensor. But the whole thing has to be coordinate invariant, so therefore you get down to the Ricci tensor. Now, the right-hand side is a generalization of the energy density. So T mu nu is a stress energy tensor measuring the distribution of matter in space-time. Well, T mu nu, of course, appeared already in mechanics before Einstein's time, and we know what T mu nu is supposed to be. It should satisfy a conservation law. So T mu nu, comma nu should be equal to 0. So in fact, this is an important point which Einstein and Hilbert missed. Namely, at the beginning, Grossman and Einstein wrote down R mu nu equal T mu nu. And that is not right because T mu nu satisfies conservation law and R mu nu does not satisfy conservation law. You need to put down minus R2 times T mu nu in order for the left-hand side to satisfy conservation law. Namely, it's divergence free. So the left-hand side putting in this term was actually discovered by Richard and also Bianchi. And this left-hand side nowadays is called Einstein tensor, but it was in fact invented 15 years before Einstein. Okay, so well, there's no doubt Einstein made a huge contribution, a fundamental contribution. So I guess it's fair to call it Einstein tensor. So this Einstein equation then relate gravitational potential, namely the metric, with matter similar to Einstein equation, Newton's equation. So Laplacian U equal to rho is now translated into Rij minus R over 2 Gij equal to T mu nu. And in the same thing, in the same token, in space-time, similar to Minkowski's metric, the particle with mass travel along geodesic, which are time-like, and the photons travel along the non-geodesic. So G mu nu defines a geometry, a Lorentzian geometry for us. You can still talk about geodesics, but there are geodesic with length equals 0 and geodesic which is negative length. And this one is timeline, one is now. So this is exact generalization of both special relativity and the general and the Newton's equation. It's a good mixture. Okay, so Einstein equation show that Richard curvature of the space-time metric accounts for matter distribution, but the content of gravitational force rests on the full curvature tensor of the metric. So the full gravitational force has to be measured by the full second-order differentiation of the metric tensor Gij, not just the contract one. So this is very similar to Newtonian mechanics. Actually, the Laplace equation is similar to this. Okay, so this is the background of general relativity. So general relativity, write down an equation which is set here, the Einstein equation, where the left-hand side is a generalization of Laplacian U, the right-hand side is generalization of rho. Okay. Now, a fundamental difficulty with the concept of a mass, which can be defined rather straightforwardly in Newtonian mechanics, is that you have a mass density, you integrate the mass density, you get local mass. But we could not have a mass density in general relativity. There's no such a concept of density in gravitation. This is because of Einstein's equivalence principle, which says that any quantity in significant quantity which are physical meaningful should be independent of choice of coordinate. If such a density exists, it would depend upon the first order differentiation of the space-time metric, but the choice of normal coordinate at each point renders such a measurement to be trivial, because we can always choose a normal coordinate of the metric so that the first differentiation of the G mu nu is equal to 0. And therefore, such a density must be equal to 0, because the equivalence principle says that it should be independent of how we choose the coordinate. And therefore, the density should be always 0. And that means you cannot integrate it, everything will be trivial. So therefore, we realized it long ago, already by Einstein himself, that a local density does not exist for gravitational energy. Now, of course, you can still define matter energy. Then, of course, there's such a thing exists because it's just enough matter. But for gravity, you cannot do that. There's no density for gravity. So therefore, we try to give a less precise measurement. Namely, we associate conserved quantity to a region enclosed by two-dimensional surface. So a two-dimensional surface sitting in space-time, we want to measure about the flux or the conserved energy that are enclosed by this two-dimensional surface. This important notion was actually was discussed long time ago, basically around 60 years ago, and Roger Penrose lists it as a major problem in general relativity. He talked about it long ago, But in 1982, I invite him to give a talk in the Institute for Advanced Study. He write down some unsolved problem in classical general relativity in the book that I edited, which is called Seminar on Dependent Geometry, published by Princeton University Press. He lists it as a first problem. Number one problem is to define what is quasi-local mass. So what is the concept of mass enclosed by two-dimensional surface? And then the second problem he would want to write down is the quasi-local angular momentum, which is the topic I'm going to talk about today, angular momentum. Okay, there are many reasons to search for the concept of local, quasi-local quantity. After all, we like to know this come of mass. We want to know what is the local mass, what is the binding energy of some bodies rotating around each other. So we already know what LIGO observed was two bodies, two black holes colliding and then create something out. So we want to know what bind them together. So without knowing what a quasi-local mass is, it's difficult to understand what the binding energy is. So also, a good definition of quasi-local mass should help us to control the dynamics of the gravitational field. Because we look at some conserved quantity, we'd like to know how this quantity would move under evolution. If we can control the evolution, we can control the gravity quite well. These controls should be quite complement to the standard energy method that we used to use in hyperbolic equation. In hyperbolic system, we like to control, we want to create energy and want to see how the energy can be controlled. And using that, we control the evolution of the hyperbolic equation. So this appear in many problems, even in the important question of stability of the Kerr metric. And there are many interesting questions. We should be happy to use quasi-local mass. So there's a long history of quasi-local mass. I don't have enough time to go through all the history, but I will describe a definition that was given by Muda Wang and myself about 15 years ago. So we want to associate quasi-local mass to a two-dimensional space surface. A surface, two-dimensional like S2 sphere, which is topological sphere, it should be considered a boundary of a three-dimensional space-time region. And so what we are trying to associate some quantity which is measuring the gravitational mass in this three-dimensional region. That's what we try to do. And we want to say that this mass depending only on the intrinsic geometry of the surface and also the infinitesimal geometry of the extrinsic geometry of the surface. And that's all. It should not depend on the three-dimensional space-time region, because we like to say that what we define is conserved. That means the three-dimensional region can move back and forth as long as you fix the boundary, we will get the same quantity. So we associate a quantity to the two-dimensional region associated with the infinitesimal deformation of the surface and its intrinsic geometry only. And in order to make it work, we assume the surface has a space-like mean curvature vector. So the mean curvature vector is a vector which measures how the surface deforms in space-time in terms of how it contrasts infinitesimally or expand. We assume that it's reasonable expanding, so the mean curvature, as a four vector, we assume the mean curvature vector is space-like. So that's the basic assumption we make. So what kind of definition do we need to use? So let me explain to you. Given a two-dimensional surface, I have a normal bundle. Two-dimensional surface, a normal bundle is 1 + 1 bundle. There's a normal direction, two normal direction, two non-normal, and therefore I have a definition of a connection one form given in the following way. I take the mean curvature vector h as I defined earlier and divide by its length, so normalize it. And then I take the J, which is reflection, future timeline vector, given by reflection of the mean curvature at H through the incoming light cone. So this is intrinsically defined. And then I covariant differentiate J mod H. This defines a connection one form for us in the normal bundle. Okay. So this is something that are given to us, knowing the fact that we have a metric and also a normal bundle. So normal bundle is an infinitesimal deformation of the surface sitting in the space-time. Okay, so this is a quantity that I'm given to myself. So what do we have now? We have three quantities: physical quantity. One is sigma, which is a metric on the surface. So sigma is a metric defined on the two-dimensional surface, which is homeomorphic to S2. Mean curvature H is a vector. You can look at it as a section of the normal bundle. Alpha H is a connection defined on the normal bundle. This triple is a quantity that is given to me. So metric H and alpha H. From here, we can define something called mass energy based on a Hamiltonian formulation of Einstein's general relativity. Is well known by ADM, Arnold, and several other people, and also by several other physicists. We know how to define a quantity. Once we have a quantity like that, and we use an isometric embedding on the surface into R3,1. And then we do an optimal isometric embedding, minimizing the energy. That defines the quasi-local mass. So what do? We embed the surface sigma with the data that are given. I isometrically embed the sigma into Minkowski space-time. For each embedding, I can define energy. And then I'm minimizing this energy. And then we found an optimal one. That's what we did. And we compare the extrinsic geometry of sigma and sigma naught. Sigma is in the original surface that we are given. Sigma naught is the one that isometrically embed into Minkowski space-time. So I'm comparing the information on the original surface with the information in Minkowski space-time. Sigma naught is in the Minkowski space-time after isometric embedding. So what do we have? The physical surface we have has this triple: the metric, the mean curvature, and alpha H. And then I isometrically embed it. I get a different quantity. Sigma is a metric, and the mean curvature vector and the new connection, because the sigma sitting in R3,1 has a new connection now, new normal bundle. So this setting we have. After I embed the reference, putting the surface into Minkowski space-time. So what is the upshot? I'm trying to compare what we have in our physical space-time with something which is trivial space-time, namely Minkowski space-time. We are trying to compare them in order to get our mass. Now I take a future timeline vector field in R3,1, which is simply the translation vector field, the constant vector field, unit vector field, which is constant in Minkowski space-time. And this defines a timeline vector field in the whole space-time, the translation vector. And then I define the embedding x dot t. So what is this? It's just a time function. The function restrict the time function in Minkowski space-time restrict to the surface. Okay, tau is a time function. After I put sigma into Minkowski space-time, I get a function called tau. Okay. Now, turns out I can define the following quantity. I define rho, which is defined in this complicated way, it looks like, but it's actually quite natural. H naught is a mean curvature vector. H is a mean curvature vector of the original space-time. I define this quantity rho. This rho is a scalar function defined on the two-dimensional surface. And then I define a vector field on sigma, on the two-dimensional sigma surface. And this set is defined by this equation I wrote down here. So this is an interesting quantity which is cooked up by the embedding, and turns out the optimal isometric embedding equation that we want is the induced metric is given to be sigma, and also divergence of J equals 0. So whatever isometric embedding or optimal is, we just need to remember this equation. We motivate this equation from the isometric embedding, but in fact, what we actually are looking for is that given a surface sigma, we solve the equation x satisfy these two quantities with rho and j defined in the previous way. Now this looks complicated, but it's actually not that bad. What this equation is a fourth order elliptic equation, nonlinear elliptic equation, and this we know can be solved. And we can also numerically solve this equation, and also we can do perturbation analysis to solve this equation. This optimal isometric embedding equation can be solved when the surface is asymptotic to a round sphere. We can do an asymptotic analysis to actually find the solution. And the quasi-local mass is then defined by the last quantity here. E sigma xt is equal to 1 over 8 pi integral rho. So let me recap again. Given sigma, we are given several quantities, namely the connection in the normal bundle, the mean curvature vector, and the metric. Given those quantities, I want to solve the equation in the middle of this page, namely dx dot dx equals sigma, where x is unknown. Capital X is unknown, is the vector value function defined on the surface. The vector value function is embedding the surface into alpha 1. And then from this embedding, I can define the quantity like tau and like rho, which I've written down here, and the alpha h naught can all be defined. And then the equation I want to solve is divergence of J equals 0. So that is what I'm looking for. So everything is in this page. Actually, it looks more complicated. I was trying to motivate earlier. Once you solve this equation, I define the quasi-local mass by the last quantity, integral rho. So the quasi-local mass is obtained by integrate of some density. But this density is defined globally on sigma. Sigma is a quasi-local surface. And so although we lose the concept of density globally, but on the quasi-local quantity, it still has a local density. So this turns out to be good, this local density. Some of this quantity was motivated and was studied by many people for a long time. One important person is Brown and York. Before that, Penrose himself and Hawking, and many people did that. So one can prove the positivity of the quasi-local mass in this form, in the simple form. This is the case where tau equals 0 was studied by C.N. Tam and Marisa Liu and myself. But this quantity turns out to be not general enough. We want to include in dynamics, space-time. So now this quantity turns out to be not 0 if I define the quasi-local mass in this way. Only in this definition I wrote down here, the quasi-local mass is good, namely it is positive in general, and yet is trivial for surface sitting in Minkowski space-time. This is the quantity which is important. I want to define the concept of quasi-local mass, which has a property that in general is positive, non-negative, and is trivial for surface sitting in Minkowski space-time. This turns out difficult to manage. And the embedded surface sigma naught is a unique surface in the case when we are sitting in Minkowski space-time. And otherwise, if it's asymptotic to the infinity, Minkowski space-time is also unique. So this is a very good definition because we have uniqueness of the surface, and when it's asymptotic or trivial, and it is not in general because we don't expect that to be true. Okay, so as I said, in a perturbative configuration, when a family surface limit to a surface to a sphere, we can always solve it infinitesimally, and we can use it to do many things. Okay, And we proved, Wang and myself proved that this quasi-local mass was able to capture ADM mass if the surface is asymptotic to spatial infinity, and capture something called Bondi-Chalmers mass when it's moving to null infinity. These are two well-known quantities which was defined by Einstein, the first one. The second one was defined by Bondi and Chalmers, measuring radiation of the gravitational force. So this is very good. That means the definition I did with Wang actually captured the classical definition when we go out globally. And also it is important because it's positive and it's trivial in the right time. Now, actually, it's interesting to know what ADM and other people did. So they look at this is actually what Einstein did too. He looked at initial data, assuming you have a three-dimensional manifold, which is asymptotic trivial, which means that outside compact set, the manifold looks like complement balls in our fields, the global coordinate, and they make the assumption that the metric on M is asymptotic to delta, the Euclidean metric, up to some fall off, and K, which measures the vibrating of the free manifold in space-time, decays like R minus Q. So P and Q are positive when R goes to infinity, and usually one assumes P is bigger than half and Q is bigger than phi over 2 to make sure the mass is well defined. This is due to ADM three authors, Arnold, Desher, and Mister. And this was actually discussed by Einstein himself. And the famous theorem due to Rickson and myself, and later by Witten, is that this quantity is positive. This is a famous positive mass theorem. Anyway, the point is that the quasi-local mass I just defined with Wang recaptured this quantity, which was defined, as I said, by Einstein already. Now, so what happens when the quantity, when the asymptotic is not quite well good, P bigger than half and Q bigger than phi over 2 is good. So when P is less than half or Q is less than phi over 2, this will have to give some interesting quantities sometimes, but even though it's not exactly valid in the case of the definition given by ADM, but in our discussion quasi-local mass, both of them are still works well. And now we are encountering a major problem is to define angular momentum. Here I'm defining mass. The mass turns out to be easier to define because convergence is easier. P bigger than half, Q bigger than phi over 2. The null infinity is more difficult. So when we look at distant observer, like what we're doing here on Earth, we point our telescope to far away, and we are sitting something called future null infinity, where we are watching out the light rays coming from the star or from a galaxy. And the light rays travel along null geodesic. And space of all these null rays is called null infinity. We are sitting in null infinity. And how to describe this null infinity for an isolated gravitational system? Isolated because we are looking at something far away. We are so it's somewhat isolated from us. And this script I plus usually was measured by several quantities. One is called Bondi-Sachs coordinate. This was due to Bondi in 1962, Sachs in 1962. And then later, Roger Penrose developed something called Penrose conformal compactification. So this is basically a coordinate choosing to measure the null infinity. See, I'm sitting in the Earth, I'm pointing out the infinity. I need a coordinate system, a depth coordinate system to measure things. And then in 1993, Christodoulou and Kahneman solved a very good problem, perturbation of Minkowski's spacetime. There he used they developed another coordinate system, which actually shows the panel's conformal configuration is more than optimal. Sometimes it's not true. Anyway, so this coordinate system, why I mention it, because I need it to traditionally, that's the way that we define what angular momentum and also the mass is. And these are idealized property, both boundary stars and panels coordinate. But anyway, following tradition, we are going to use the boundary Sachs formulation here. So let's see what it says. The Bondi and his collaborator postulate a coordinate system with a good motivation based on the wave equation, classical wave equation. They said, let's try to write the metric tensor, the Gij, gravitational potential, in this form. So this is a metric tensor, Lorentzian metric tensor written in this form, where U and V are asymptotic flat in the sense that both U and V is asymptotic to 1. And HAB, which is defined on the sphere, is on the two sphere, is asymptotic to the standard metric or the round sphere sitting in R3. And we want WA to be asymptotic to 0 as R go to infinity. So when R go to infinity, U and V go to 1, and HAB go to the round sphere, W go to 0. So when W equals 0, HAB equals to round sphere, U equal to 1, this is exactly the Minkowski space-time. So this is a rewriting of Minkowski space-time in this metric, but we are dealing with an asymptotic form. So Bondi wrote down a condition for the U, V, HAB, and WA. He wanted to expand in the power series of 1 over R. R is going to infinity. We write a power series of expansion of 1 over R. And then Bondi and several of his collaborators found that the physics of gravitational field are encoded in the coefficient of this power series expansion. The dynamics of the gravitational radiation is encoded in the quantities U, V, HAB, and W. So which I'm going to tell you now. So this is getting somewhat complicated, but we have no way to avoid it because angular momentum turns out to depend on all these quantities. So let's first of all see what Bondi did. Well, in the Bondi-Sachs formulation, that means I write down the metric in that form. So that form is called Bondi-Sachs coordinate. That the fact that I can write the metric in this form is called Bondi-Sachs coordinate. Okay? Okay. Well, V is written as 1 minus 2m over R. So MUX is supposed to be bounded quantity depending on U and the X. X is the space variable plus big O, R minus 2. Okay? And this guy is called the mass aspect, defined as I plus. The Bondi-Charman energy momentum is a 4-vector defined by E, PK. So U is a constant slice where we associate with such a U is a constant slice, is a 3-dimensional slice, and we associate this quantity E and PK. E is the Bondi mass. So integral of M is called the Bondi mass, okay, or energy. PKU is a linear momentum, which is obtained by taking MUX dot with the position vector. Okay, position vector is defined here by x tilde 1 equals sine theta cosine phi. Okay, so this is a famous Bondi-Charman energy momentum that we use, and this is used in the study of general relativity in general. Okay, so all this one come out from V is only one of the quantities that appears. You see, in the metric tensor, we are UV, and I'm using V only so far. So from V, we define MUX, and MUX I define what E is and also P is. But this is only for the energy momentum, but we want to go to angular momentum. This becomes more complicated. But before talking about angular momentum, let's look at the mass. So the energy EU, I want to see the dynamics of it. So EU is equal to quantity I just measured, and I want to differentiate it. This EU are differentiated by the U and see how the energy moves under the dynamics. So it turns out it was computed by Bondi is equal to -1/4 of integral n squared. Now n squared is a square, so it's positive. So what Bondi found is that the Bondi energy actually decays in U. When the dynamics move on, the energy goes down. The Bondi energy goes down. So this was interpreted as the energy radiated away by the whole system. So when you go to E infinity minus E minus infinity, you get this total quantity. And this n is something called mass function, which I'm going to define to you now. But anyway, this is a famous Bondi loss, mass loss formula. It says that energy will go down when the things keep on radiating away. And this is compatible with what physics wants. Things will radiate away. And the measurement of how much it radiates away is given by this quantity, the E infinity minus E minus infinity. So what's n? Now n has to come in from the HAB. HAB, you remember, was the metric tensor defined as sphere as 2. So it's given HAB is equal to the sigma AB, which is the metric on the standard sphere, plus some lower order term, 1/r CAB UX plus R minus 2. So there's a symmetric and traceless 2 tensor. CAB is a shear tensor, and a differential to U is called the Lewis function. It's called by Bondi to be Lewis function. So we look at the distortion of the sphere. When we go out to now infinity, it distorts around, and we measure it by a tensor, and the rate of change is called the Lewis function, n. So the capital N written in the top is the norm square of this tensor. Okay, so the Lewis function actually controls the radiation of the whole system. Okay, so Bondi mass is measured by the change of this Lewis function. Now let's take a look now. The symmetry of this now infinity, as I said, is a group. It's called Bondi-Meissner group. BMS group is a famous group. And these are coordinate transformation at now infinity, which keep the Bondi-Sachs coordinate form. So I take coordinate change, and I want the coordinate change still make sure that the Lorentzian matrix still has similar form. It's called BMS group. Okay, so I insist my metric tensor has that form. So this defines the group. And turns out there's no preferred coordinate system in general spacetime. That's what Einstein do not allow preferred coordinate system. So therefore, whatever quantity we use, we want to make sure it's independent of choice of the Bondi-Sachs coordinate system. Okay, so anything that is interesting and well defined in physics has to be independent how you measure it and how you measure the Bondi-Sachs coordinate. Okay, now there's an important coordinate change in the Bondi-Sachs coordinate or BMS group. Is I do a simple thing. I just move U. U is one of the coordinates I use, U and X, and U equal U bar plus Fx. So I take any function on X on the sphere and I move it. And it turns out this still preserves the form of the Bondi-Sachs coordinate. After you change the coordinate U by U bar plus Fx, we still form a Bondi-Sachs coordinate, no difference. So such a change, we call it supertranslation. Supertranslation because it's translation, but F is arbitrary function. Any smooth function can, any function can appear at that. Now, under this transformation, the mass aspect which I've written down, M, U, X, And the shear tensor, CAB, which I write down, is rather complicated, turns out. And however, the transformation of New's tensor is reasonably simple. The one I just wrote down here turns out to be reasonably simple. So CAB is somewhat complicated. NAB turns out to be reasonable, simple. And then using that, we prove that the total energy radiated away compared U coordinate is the same as the one in U bar coordinate. So therefore, there's no ambiguity for the energy radiated away. So because it is simple, the way the n is changed is simple, the whole right-hand side is simple, can be transformed nicely. So the boundary energy transform away is well defined, no ambiguity. But then, first of all, the Wang-Yao mass that I just told you earlier turns out it recovers the boundary mass, so it's fine. Because we can actually calculate it, the surface isometric embedding has a unique solution and all that, and the limit of the quasi-local mass recover the boundary Chalmers mass. And so we can actually, in this form, prove the non-negativity of boundary Chalmers mass. The proof of the boundary Chalmers mass turns out to be actually non-trivial. The most proof actually has some possible concern, not rigorous enough. But this proves that using this way is actually more rigorously. And the process is robust and will carry out in any asymptotically hyperbolic initial data system. And even if the now infinity is rough, and we can still do it. Now, so mass is fine, and energy is fine, everything is good. But the definition of angular momentum, that was one of the key points of this talk, is much more complicated. But this is an important thing, because the angular momentum is the one supposed to be the one who carries the gravitational radiation away, give it away. And this was discussed by many authors. I mean, you are talking about maybe 20 authors in a different time in the last 60 years. And one important author, closer to what we have here, is defined by ds. It's called, let's call it ds angular momentum of a u cut. U is a three-dimensional cut, and it's defined in the following way, where y is a rotational field. So on the sphere, is a rotational field. Na is the expansion of w. So remember w is one of the vector fields that define the boundary Sachs coordinate, and they formulate such a thing. And this whole thing here is called the angular momentum aspect. This was discussed by many people in a different form. Now, first of all, let's come back to the important question. Roger Penrose in 1982 says the following thing. He said the very concept of angular momentum gets shaped by these translations, super translations. The super translation I mentioned, u bar plus fx defines the shape. And it's hard to see in this circumstance how one can rigorously discuss such a question as the angular momentum carried away by gravitational radiation. He said things are dependent coordinates, dependent on super translation. It's not clear what we are talking if we said about angular momentum carried away. So what he is referring to is that in one boundary Sachs coordinate, you can define the angular momentum, J, theta, and you want to look at the total flux related to the new coordinate system after you super translate. So the question is, what do they do when you move around using different coordinate system, namely obtained by translation? Well, we look at the thing, and then first of all, let us talk about W. W is one of the vector fields that appear in the boundary Sachs coordinate. We do expansion. It turns out have this form. So 1 over r squared and 1 over r cubed. The coefficient looks like that, and then 1 over r form. So this appears in the boundary Sachs coordinate. So remember, look at W, and Na appears. Na is going to be an important quantity for us. Okay, this appears in the angular momentum. So appear 1 over r cubic term. That's why it's tricky. And in this form, C is the one that we defined before. Now we appear NA. So in 2021 last year, we assumed the New's tensor NAB decays in a reasonable way, like U to the power -1 minus epsilon. And assuming that two Bernoulli sex coordinates are related by supertranslation. That is the question we have been trying to do. I move one coordinate system to another coordinate system by supertranslation F. So I measure the flux, delta J tilde F minus delta J tilde. Two different flux measure in a different coordinate system. We take its difference. It turns out to be equal to the right-hand side. So let's explain what this is. YA is the rotational vector field, and it is differentiating the M plus minus M minus using the rotational field. What is M plus? M plus is a mass aspect that we defined before. Assuming U go to infinity is M plus, U go to minus infinity is M minus. So I take the mass aspect one, and now one at infinity, one is minus infinity. And then I multiply by FL less than equal to 1. What does F less than equal to 1 mean? A supertranslation is a function has many modes. You take a spherical harmonic expansion. You just take the linear part. Linear part, you see, you take a function like Fourier analysis. Fourier analysis tells you a function can expand in Fourier mode. You take the constant and the linear part. Here, FL less than equal to 1 is the constant and the linear part. So we demonstrate that we can find such a formula. And this is very good because F less than equal to 1 is just a linear part. And therefore, we can conclude a angular momentum in the following way. So this is what we proved. And this is very good because this is exactly what you expect for the ambiguity. Because the total angular momentum is not supposed to completely invariant under supertranslation, even in classical Newtonian mechanics. Because center of mass and all these are changes, and when depend on linear momentum. When the angular momentum is changed, it depends on the movement by linear momentum. Okay, so this is exactly FL less than equal to 1 is related to linear momentum. So that's fine. This ambiguity. Now let me tell you exactly how we come up with this definition. How we come up with such a formula. This statement we just proved. So first of all, I have to tell you what quasi-local angular momentum is. In general, a quasi-local quantity is defined by this integral. On the surface, I take rho, which is defined with local quasi-local mass density, and J is the vector field I defined before. I take any Killing field in alpha comma 1. In this case, it's actually a rotational vector field. And I do this integral, and I get a quantity. This is called quasi-local angular momentum that we have here. Okay, so this is a quasi-local angular momentum that we define. And so given a configuration which is not going to infinity, I can define angular momentum. It's said to have many important invariant properties, and we take the limit of this quantity to infinity. And this will be a total angular momentum with the invariant property that I want to use. That's what we did. So when we compute the limit of the quasi-local angular momentum in boundary coordinate, we come up with this consequence. Namely, on the bottom, JUY is equal to integral YA. NA was the quantity I defined earlier. CAB is the New's tensor, the differentiation of the equivalent New's tensor. And then we have a function called small c. Small c comes out from the decomposition of capital C into several parts, harmonic part and the divergence part and all that. Okay, this quantity C is defined on the sphere in a global way. This quantity actually has never come up in any definition of angular momentum that was done by all the other people, although there are more than 20 people working on this field, but they did not discover this function C. That's our contribution. This C is a non-local term in the sense that only it depends on the sphere. But on the other hand, this plays a fundamental role. That's the reason that it comes out to good using the C. We can find out this supertranslation invariant on angular momentum that we define. Namely, if the new function decay in this way, if I define F to be what I said, the constant plus the linear term, this is the kind of rotation part of the supertranslation, and the higher part disappear, turns out, in this ambiguity. So what we found out is the total flux of angular flux linear momentum of the angular momentum we define is measured by the this linear change times the total flux of body flux linear momentum. This is a formula very similar to what Newtonian mechanics says. So when we move the angular momentum from one coordinate to another coordinate is different by linear momentum. So that's what this formula says. So it comes up with exactly like what we learned from Newtonian mechanics. And so I think this pretty much solves the problem of ambiguity of supertranslation ambiguity for angular momentum. So our proof actually is largely geometry, and we motivate. Some part is motivated by physics, but largely the whole argument is based on geometry. And these are non-trivial procedure to do all this. And of course, it depends on a large number of analysis too, and a huge number of combinations was involved. So in conclusion, we have found a complete set of 10 conserved quantities in general relativity, the energy, the linear momentum, and the J, which is the angular momentum, C is the center of mass. All these things define a classical conserved quantity in classical mechanics. We have been able to recover it for general relativity, which is not trivial to define, and it defines now infinity, which should be observable. And it turns out all these quantities satisfy the right condition that if we measure everything in Minkowski space-time, all these quantities are trivial. This is a non-trivial statement because you take a surface in a two-dimensional surface in free space-time and you measure all these things, the limit is all could be very different, but we prove that it's trivial. If we're sitting in the trivial Minkowski space-time, and in the case of curved space-time, we found out that pk and ck vanishes, and the E and jk recover the mass and the angular momentum, which is defined in curve metric. Curve metric is well studied, and everybody agreed that what Kerr did is excellent and adaptable to the physical phenomena. So it's important to recover what they have. So we do recover them. And we proved that for general space-time, the total flux is translation, supertranslation invariant, and then their flux transforms according to basic physical law under ordinary translation. So that's what's similar to what Newtonian mechanics tells you. So there's a lot of detail which I have to miss, but I think I hope that I have explained to you what we have done in the last couple of years about classical Newtonian quantities be generalized to the general relativity. And I should say, even in the time when Einstein and Hilbert was working on general relativity in 1915 and 1916, these questions are in their mind because all these classical quantities they were hoping to recover in general relativity. They do encounter difficulty, and we were able to solve it. Yeah, thank you.
Much for that, Mr. Yao. Unfortunately, we have only one final question. Пожалуйста, подойдите.
is your definition of quasi-local energy is additive? I mean, if you have two intersecting surfaces, if the quasi-local energy of the sum of the surfaces is equal to the sum of energies for each surface. And the second related question, suppose you have a closed universe. I mean that every spatial section of space-time is compact and without boundary. Does it have energy and angular momentum?
Okay, these are two excellent questions we consider. Additivity is tricky because we are thinking two-dimensional surface space-time. When you say two surface additive, it becomes a tricky question because if you want to put this two-dimensional surface, fold them in the three-dimensional space-time hypersurface, that is somewhat difficult. For example, if you take a three-dimensional space-time surface to be a linear space in curved space-time, and then it's much better sense to talk about additivity. When the two-dimensional surface are not sitting in a chosen or preferred three-dimensional slice, this becomes far more complicated question than what it sounds like. And we are trying to study it, and we think there's some sub-additivity probably, but not exactly additivity that you expect. Okay? So that is something we need to explore. The second question is that we have to look at the model space. The model space, right now we are using Minkowski space-time, so everything is non-compact. We can also model after anti-de Sitter space-time, there's no problem. And but then we have to model after de Sitter space-time for closed universe. These are interesting. We make some progress on it, but we have not completely concluded the best that we can do at this moment. But I think it's an excellent question. We are still looking into that for a closed universe.
Thank you.
Thank you very much, Professor Yao, and thank you again.
Thank you. Thank you very much for the invitation again. Okay, bye.